All right, welcome to the last silo seminar of the semester. It is my great pleasure to have Professor Yao Xie from Georgia Tech as our speaker. So Professor Xie is the Coca-Cola Foundation Chair and Professor in the Industrial and System Engineering School in Georgia Tech. She's also the Associate Director of the Machine Learning Center in Georgia Tech. She has done many interesting work in the intersection of statistics, optimization, and machine learning. And she also has a long list of accolades that I'm not going to repeat, but it includes a career award, various awards from the IEEE Information Science Society, etc. So today, Professor Xie is going to tell us about minimax optimization in Wasserstein space. Take it away.
Okay, I guess the speaker's on. Thank you, Yudong, very much for the very kind intro and invitation to be here. It's actually my second silo seminar. The first one was online. I think that was during COVID. So very happy to be here in person and see everybody's face here. This is very nice. Okay, so today I would like to talk about recent work on how to do worst case generation, basically, through this minimax optimization framework, but it involves Wasserstein space, which is a space with continuous distributions and also the decision. So the work is going to be based on this, roughly speaking, these two papers. The first one is this paper. We introduced this notion of flow-based, which is a type of generative model-based distributional bus optimization. And the second paper, actually, we just posted on arXiv. It just came out this morning, just on time. So if you're interested, please check it out. And joint work with my collaborator, Professor Chen at Duke Math, my postdoc, Linji Zhu, who's on the market this year, and my student, current student, Inchi, and the previous student, Chen. Okay, so the motivation from this, I start with the robust optimization. Basically, I think this is a very classical type of research in optimization where there's uncertainty. For example, when you solve optimization problems and you have, how do we use data is typically we use this data to estimate some parameters in the decision-making problem. And the data is finite, it's noisy, it's not perfect, so the estimation is not perfect. This introduces the uncertainty in the optimization problem. So to make it more robust, basically, is we want to account for such uncertainties by introducing some uncertainty sets, right? And so there's, classic books on this topic and so on. And in particular, in this talk, we're going to focus on distributionally robust optimization. Means that can we not making any particular parametric assumption, but directly model uncertainty on the distributions. It's also a classic line of work on this. And in particular, we can consider this popular formulation, which is Wasserstein DRO. And so in this particular formulation, right, this has been studied, for example, there's many people on this topic. Recently, there's the survey by Kuhn et al. And Blanchett and et al. And so this is a minimax problem. And in this problem, you say that I want to make a decision So theta represents the decision. For example, you have a classifier. The theta then is going to be the parameter of my classifier of my neural network. And then you want to minimize some loss. But at the same time, instead of minimizing the empirical loss, empirical risk minimization, but this is going to consider the possible worst case loss. And so the worst case is going to be captured through this maximization over some distribution Q. And this Q is going to be not the distribution of the data, but a distribution that's close to the P. P is my data distribution, for example, in some metric. Right? So in order to describe the distribution uncertainty, we introduce this uncertainty ball centered around the distribution P. And so there are two things involved in definition of the uncertainty set. First is how do I define the metric, right? So how close P and Q are. And second is, of course, the radius, right? How big of uncertainty I want to consider. And then in particular, if you choose the metric to measure the distance to be Wasserstein distance, I'm going to talk about what it is next as well. And then this give us the Wasserstein DIO formulation. And the objective function is going to be expected loss. And this loss is, involving this little l. That's our loss function. For example, in classification problem, this is going to be the classification loss, right? And then theta is our decision, and x is our data. And then you consider expected loss x following some distribution q. This q is somewhere near my p. Okay, and okay, so this is the DIO formulation. And so, right, this is the uncertainty set, Wasserstein uncertainty set with radius r, some reference measure p, which is the information coming from data. Okay, so what is this Wasserstein metric? Roughly speaking, this is the distance defined between two populated distributions. And so it becomes popular. I think part of the reason is because this is a very general definition that can measure the distance between two distributions that can have different support. Okay, and so because of that, you hope this can include a richer class of distribution to be considered within that uncertainty set. And so I put two definitions. The first one is the Kantarovich formulation, and the second one is the Monge formulation. And so roughly speaking, what this is you would say that if I give you two distributions, I want to consider what is the smallest effort to make one distribution look like the other distribution. So in that sense, it's also called Earth mover distance. And so in this talk, actually, I'm going to focus on the second definition, which is the Monge formulation involving a push-forward operator. And I will show that this gives us, a convenient way to develop both the algorithms to solve my minimax problem. And the second is this actually enables us to perform some analysis that involving distributions. And these two definitions are equivalent due to the so-called Bernoulli theorem. And this is, under some very general conditions, they are equivalent. Okay, so next I'll explain. In this formulation, I use Wasserstein distance to define the uncertainty set. Why Wasserstein? Instead of, for example, why not use the KL, for example, Kalbach-Leibler divergence between two distributions? So if I use Kalbach-Leibler, and so that means I have to consider something like log of the P over Q. And so because of this involves the ratio of the two distributions, that means they have to sit on the same support. And so, and this actually means that if I define my uncertainty set using KL, then I only consider all the Qs that have the same support as my P reference measure. And what is P typically? Think about, for example, I want to develop a robust classifier, then the P is going to be all the training data I have collected. And that's a bunch of pictures, for example. And in principle, it's basically discrete distribution, right? So I can maybe make it smooth or something, but in principle, it's discrete distribution. So this means I only consider, the same set of images, I change the weights on that. So this, in some sense, like people think it's not generalized enough because you will not consider anything that can be different from the training data. But the Wasserstein doesn't have this problem because if you look at the formulation here, it basically allows you to measure two distributions that has different support. Okay, so we'll revisit this a little bit more. And so for the Monge formulation, let me explain, roughly speaking, how do I understand this? It involves something called a push-forward operator. So this is a map that maps the data. For example, if my data is d-dimensional from RD to RD, and then I want to find this transport map, right, that tells me how do I move my data points, such that this map will first couple the two distributions. And so it means that if I start from some distribution P, when I move the distribution, I want it to convert the distribution into some distribution Q. And at the same time, it will minimize my transport cost. Okay, this transport cost is defined as, for example, Wasserstein 2, right? You can have different metrics for the transport cost. This is the simplest one. It's Wasserstein 2. And just look at the displacement under my transport map, right? And take the square of that, expected the square distances. That's my transport cost. So roughly speaking, this is try to find the map that will, meet the two, endpoints, the distribution requirement. So this push forward operator, and such that you minimize the transport cost. And so another thing I want to differentiate is you can see this is a mapping. That's not a simple function, but this is a vector valued mapping, right? So the input is data dimension, the output is also RD. This means that I basically move a d-dimensional vector to another place in d-dimensional. So it's literally a transport map. And another thing is this happens to the data. And so this push forward, the sharp sign, and whenever I see this, I feel like this is like a music sharp. The sharp sign basically says, this is, if I change my data, then the underlying distribution of my data is also changing. And so this is called push forward. That's mapping distribution from P to Q by operating on the data itself. Okay, so with all the basic setup, now let's try to see what's going to happen if I want to solve this minimax problem. Okay, so there's a lot of work being done in this domain, and in particular, a lot of, the challenges coming from, people have lots of solutions, but one of the particular challenges actually to handle this Q, right? This Q is my distribution. And when we introduce the Wasserstein uncertainty set, we're hoping that it includes many possible distributions in my set, even if my P is discrete, right? We want the set possible to include the continuous distribution. But here comes the challenge, which is if, usually the problem we're able to solve is only for the P that is a discrete distribution, okay? And for a few reasons. And so, first of all, right, if you choose the P to be the P hat empirical distribution, okay, so imagine you have the uncertainty set centered at some discrete distribution, and the discrete distribution is like a histogram of all the energies you have collected. And then turns out, after some reduction, nice reduction by, some, and you will show that the Q star that's going to be the solution of my minimax problem is also discrete, okay? And so then you take a step back and say, wait, I start with a discrete reference measure. I try to solve a problem of the set that includes possibly all the distribution, including continuous distribution, but it turns out the solution is degenerate. It still is a discrete. So that's a little bit problematic, right? This is my example shows what it looks like. And in this case, I have 5, data points, and then I try to find the worst case distribution. Then it's also basically going to be another set of discrete points. Maybe I change the weights on it a little bit. So it's sort of like this is a little bit of, counterintuitive, right? Not achieving the goal I want it to be. And the second is, in order to solve such a Q star that is discrete and extractable, first of all, good news. Yes.
For example, do we assume that the L is convex or strongly convex, or it is not even necessary?
Oh, great question. Okay, so thank you. So I should clarify that in order to derive this result, you have to assume a convex-concave structure. In order to have strong duality, you can switch min and the max. But then in the paper I'm going to present today, we want to go beyond that and talk about non-convex problems, because you can imagine even for training neural networks, right, the classification problem is not going to be convex. Okay. Yes, thank you for the question. Okay. All right, so to find the Q star and involve solving an LP linear program. And the complexity, okay, first of all, is polynomial, which is good news. It's not NP hard. However, the complexity is very high. The complexity of this LP is going to involve on the order of n to the 3 variables. And what is n? N is the sample size. This means that even if I want to apply this on a problem with handwritten digits, I have tens and thousands of digits, and this n is tens and thousands. N to the 3 is very, very high. So even if you have the best LP solver, it's going to take a while. Okay, so it's not very scalable to large data set. And so because of that, we're thinking about can we develop an efficient way to find this Q? Okay, so where hopefully doesn't have this issue, and hopefully can help us to find a continuous Q. But I have a challenge. First is, how do I represent my continuous Q? And the second is, how do I find it? And I also want to give some motivation, like why we bother with finding the Q is, I think there's important motivation because we want to have some idea what the worst case distribution looks like. And so, for example, a lot of the problem involving finding the so-called scenario generation, for example, we want to develop an algorithm for self-driving car, right? So we collect a lot of training data. These are, hopefully many representations of the scenarios that the car is going to face when it's on the road. But as you can imagine, we want to make this very, very robust. And even if there is an OOD, not a sample that we haven't seen, but the algorithm somehow is already built against that worst case situation. And there's also a rise in healthcare algorithm, right? You want to deploy an algorithm on predicting the risk of a patient in ICU. One of the projects I have is with Emory Hospital, and actually they're very interested in using some of our predictive algorithms to monitor the patients, in particular for so-called sepsis prediction. Sepsis is one of the most dangerous conditions, and that happens very quickly. Whenever it happens, it takes only a few hours for the doctors to react. So they really want to predict that quickly. But then if they have an algorithm, right, this is a machine learning algorithm on the patient, the doctors are very concerned how robust the algorithm is. If you say, I only have 100 patients' data, a lot of times you don't have a tons of data. And then they want to say, can you make it robust? So same thing here. And so if you have, for example, worst case distribution, then using this minimax formulation, we hope to make our algorithm robust. It's not just trained on the data we have seen, but also trained on the data that possibly can be worse. Yes.
I agree with the example.
Yes.
I have zero intuition why the worst case Q, if it is discrete, I don't like it. If I was careful before, you say that somehow you don't like the fact that my worst case scenario, my stress test, is discrete.
Mm-hmm.
And I somehow I don't understand that. Like, I have an initial histogram. My worst case was again a histogram. Why sentimentally or semantically?
Sentimentally.
Yeah.
I think the concern is basically, of course, you have discrete in, discrete out in a sense. And so discrete out means these are only possible, finite possible number of scenarios. And then I try to apply it on a test sample. And the test sample is not any one of these. Right? And then you have to somehow worry about generalization. And the result, a principle, the method, you could say, let's do some kernel smoothing. Okay. We can do that, but I want to have a principle way of doing that.
I got you.
Yes, great. Thank you for the question, clarifying. Yeah, and the last example is power system, of course. I mentioned this because I have a collaboration with Argonne National Lab, and there my collaborator, Dr. Chiu, is very interested in studying resiliency of the power system. Again, if you want to say, we have collected our data on how the power system have outages when there is a hurricane. But what if there's an even worse hurricane? What's going to happen? So because of all of this, we hope to have some kind of knowledge or characterization of the worst case distribution. And even if we don't know exactly what it is, but can we generate some sample out of it? Okay, so that motivates us to think about developing a worst case generation. Okay, revisit the problem. All right, I'm going to develop an algorithm using some inspiration from generative models. Okay, so start with the original formulation, right? So this is our minimax problem. And so this basically introduces a constraint that says my Q is in the uncertainty set centered at my chosen reference measure P. This is where I include my information about the training data with some radius R. And so this basically, if you write it out, is like a constraint, right? So Wasserstein 2 distance between P and Q is less than R. And so I can use my basic, Lagrangian formulation, move this constraint into part of my objective function. Then I have this formulation. So again, with respect to theta, fast decision against the worst distribution and the loss. And here I have this regularization or penalty term that basically measures how far away my Q is from P. And so this lambda is my Lagrangian multiplier, and R, the radius R, and the lambdas are related to each other. You can use either of the characterization, right? So in this formulation, we're going to consider the lambda formulation. You can show they are equivalent. And we showed that actually in the earlier paper that now I want to capture my Q, right? The main idea is basically I can capture my Q as some T. T is the push forward on this P. Okay, so if you recall from my Wasserstein definition, this basically says if I move my data points in a certain way, this will change my distribution. And this T basically then become my objective, my decision. How do I move my data such that I will make my distribution towards the worst distribution? And so you can formally show that this problem in the original formulation is equivalent to this minimax formulation that involves the T. The T is in the L2 space. So roughly speaking, it basically says I have to find this T and that have some boundedness and it's back to reference measure P. And at the same time, right, this is my original objective. Think about this as a classification loss and this regularization term. And roughly speaking, you see this is the amount of movement, squared movement. I'm going to focus on solving this problem instead now. And why do I want to consider this formulation without the transport map? Is because there is an efficient algorithm. Okay, so first of all, I'm going to talk about, let's still focus on the formulation itself. Then I talk about the implementation. Okay, so now this formulation involves the theta and the t, right? I think I write this as mean. Sorry, this should be max, and then mean with respect to theta, max with respect to t, and then this problem. And so to solve the minimax problem, right, one of the defaults is I can use some gradient descent type of algorithm. For example, GDA, gradient descent ascent. So because one is mean, the other one is max, so I can say let's go in the direction to minimize with respect to theta, and then alternate with the gradient ascent with the t. So GDA. All right, so seems like the first candidate is this. And what is going to be the gradient? All right, I have this abstract notion of the t. I haven't talked about how to capture that, but let's just talk about conceptually what happens here. Okay, so what is my loss? My loss function involving two decisions. One is theta, other is t. And then let's read inside. Inside here, I have expected the loss with respect to x following the p. P is my reference measure. Remember, this is all the training data information. And then this regularization term. And okay, so first of all, how do I take the gradient? The loss function is back to the gradient of the theta. This is a vector, so this is easy. I don't know how to do gradient descent. The second term is gone, so it's going to be this gradient. So what this says is basically I can evaluate my gradient of the loss, and then I can evaluate on my reference measure. So this is easy. This is just involving the training data. And what about the t? T is a little bit problematic. Remember, t is a vector mapping of RD to RD. And then it turns out you can still derive the gradient. And so this basically says take my loss and take it, it has two arguments. One is theta, the other one is a tx. What is tx? Tx is if I give you a candidate x, this moved it to another position, right? It's displacement. And so I treat this argument as v, and then take the gradient back to the second argument, that is my gradient. But then you plug in the tx in here. So this means that if I give you any x, I can evaluate the tx and plug into this expression here. So that's my gradient. And the second term actually is very, very simple. Okay. And because the original form is quadratic, so you can show it actually given by this expression. So the gradient back to t is defined in this way, roughly speaking, and pointwise respect to all the x. So this is p almost surely you can show that. Okay. And all right, so we can do GDA, like I said, gradient descent, ascent, alternating minimization. And then a natural question to ask is, why not just solve mean and the max? Okay, sorry, apologize. This is mean max subtract t. Okay, and so why not solve the mean max? And in fact, does this correspond to the elimination scheme or double loop? Right? You could say that instead of do alternation, I could say let's do one iteration here, but then you do many iterations inside to solve the t instead. And in fact, this actually is a strategy similar to a paper in Ducci et al. In 2018. It's very influential paper, has a lot of citations, which is developed for adversarial learning. And there they did this, basically. But the difficulty with this is, in fact, you show that for some special cases, like when L is strongly convex-concave, you can try to solve the T star. The T star is given by this expression. So this is basically saying take my loss, take the argmax to the second argument, and then pointwise, right? If you solve this pointwise, it's going to give you some kind of optimal transport with respect to some certain given theta, right? And the inner maximization problem. And this is so-called the Monroe-Yoshida regularization, or Monroe-Yoshida envelope of my loss function L. And so in applied math, actually, it is well known that this may not always be easy to solve. In some special cases, you can solve this, even pre-compute. But if I give you some general loss, it's not easy to solve. Okay, yes?
Sorry, I want to understand again the landscape.
Sure.
The L, do we agree that would be strongly convex as far as theta or not?
I will present 3 results later, actually involving both strongly convex in theta and second PL in theta, which is not, yes. And the third is non-convex.
Now my question is, because I'm not very good in functionals, is it the case that as far as T is also strongly convex, strongly concave, as far as the T
it's not the T operator.
Yes.
Yeah, the condition for the T operator is going to be very interesting because the T part involving distribution. So we're going to show that that's where the juice is going to come in. So we want to consider a case where you have some non-convexity in T as well.
So
right.
To phrase my question simply, if you have strong convexity on theta and on T, I don't understand why we don't just do.
No, we're not going to assume strong convexity.
Okay.
So this is the existing results. Yeah. So thank you. Yes, great. Thank you. Okay, so hopefully that gives you the motivation, right? Okay. Still conceptual, right? I say, okay, in principle you can do this gradient descent, GDA, but then how do you actually do it? Like you said, T is a functional, it's RD to RD mapping, this is not a vector. How do I even represent it? How do I implement this? So the reason actually is we realized you can actually use the generative model to do this. Okay, let me take a little bit digress and think about what exactly is involved here. So remember, we want to find this Q. This Q is a distribution, possibly continuous. That gives us the problem, right? Because continuous distribution is a functional. It is infinite, essentially we're solving infinite dimensional optimization problem, right? So it's not a vector case. And so let's think about how to represent distributions, right? So if I can take a parametric representation, like usual statistician would do, and then you would say, let's pick Gaussian or something, and then I can try to find the parameter of the Gaussian. But now we're not doing that. We're considered non-parametric approach, but it is also not a standard non-parametric approach because in non-parametric approach, you can represent things in kernel space and so on, but the difficulty there is usually it has the curse of dimensionality. And so not taking either one of these approaches, but essentially what we're going to do is try to cast the representation of the Q, especially the T, right? The T is transpose forward, using the idea of generative models, okay? So what is generative model? I'm sure we all have experience now, right? GPT is a type of generative model. And there's a lot of, programs like, for example, Banana, right? You can generate lots of cool pictures. And so roughly speaking, I think you can think about generative model as an implicit representation of distributions. So this is the essence of the idea is we want to represent the Q implicitly using some generative model. And so roughly speaking, you have collected a lot of data, like pictures of the birds and dogs, and they're sampled from very complicated high-dimensional distribution. I don't know what it is. And so the generative model, without learning exactly the distribution, what it is, but can generate lots of samples and following the same distribution. So that's the idea. You can sample from it, although you can still, cannot do it, know exactly what it is. Okay, so here I would summarize the generative model, broadly speaking, as a transformation to the data, right? So a lot of generative model, for example, there's GAN, all the way from earlier version of GAN, VAE, or Schnauz encoder, and the more recent version, like diffusion models, normalizing flow type of, models. And they all, roughly speaking, is a transformation of the noise towards a data distribution, okay? So that means, this transformation is going to be learned and represented using a neural network that can capture the complexity of my data distribution. And so if I can do this, then I can take a sample in the noise and convert it into a sample of a cat, right? And by the way, this is my cat. So, okay. So we're gonna, try to think about how do we develop a good representation of the T and incorporate into my GDA scheme. All right, so in particular, in these diffusion and flow-based generative model, is basically going to represent this T as a continuous dynamic version. Okay, so what does it mean? So here it involves a little bit of idea coming from statistical mechanics. And then you'd say that suppose I have some data points, these are the so-called particles, sampled from some distribution P. And I'm going to move my data points according to some velocity field, V. This V, you can think about as the arrows that characterize where you're going to move the data points and in what magnitude you're going to move them. And so instantaneous, so this is it's the speed, right? The speed is going to be this vector. And so the velocity field is the RD to RD mapping. And you can have the velocity field that differs for each location. So depending on where the particle is, the velocity field is different. And it can also change over time, right? And so, but hopefully, right, if you can imagine if I move the data points in a certain way, and then it's going to change the underlying distribution towards some distribution. In many generative model, this distribution is going to be Gaussian. But in our problem, it's not necessarily Gaussian. But we hope to use this Q to represent our worst case distribution. Okay, so in a more formal way, if you change the particles using this velocity field, and then the distribution itself is going to evolve according to this continuity equation. So you can see, roughly speaking, right, this V is what I can control. I can decide how to move my particles. And then it's going to drive my distribution. The dynamic is going to in this, following this law. And so you can think about this as a control problem to some extent, right? I start with some P, this is my data distribution, and then I can choose my velocity field to drive it gradually towards the Q, which is my target distribution. In this case, I want my Q to be the worst case distribution. That's the idea. Okay, so next one. And so why is this a good representation? Because if I have that, right, so people think about like why nowadays diffusion models and flow-based model have good performance on large-scale images, high-dimensional data, is because of the neural networks can capture high dimensionality. Okay, so in this representation, essentially discretize time, and then this V is going to be represented by some neural network, in particular RAS block. And then if you integrate this over small time intervals, essentially this tells me how I move my data. Right? If I discretize into many intervals, each one of them is a small time interval. And my big T, N, from the beginning to the end, is going to be the function composition of each little interval. And each of the little intervals is in here. And so this is actually the idea behind the so-called neural ODE, right? So you represent the transparent map using the velocity field. Yeah. Okay, so, all right, now let's tie everything back together. Okay, so why is this helpful? Right? So now we have this nice generative model. We know it can do amazing things, generate amazing pictures, handle high dimension data. We're hoping that if we use this idea to represent our worst case distribution, this can do the similar thing. Okay, and so for example, right, I take this idea, represent my velocity field using a sequence of neural networks, and then I perform, just composition from the beginning to the end. It's going to give me a transport map that I want. Okay, so my representation is going to be using this V as my velocity field.
Can I ask a quick question? Out of curiosity, why T of X does not have minus X0? I would expect that T of X is just the X1. But you take the integral, so...
You mean this one?
No. Even in the next one.
Mm-hmm.
Trying to follow a little bit the two slides, I would expect that T of X should be the integral 0,1 V of X T, comma DTT.
Oh, you're talking about
zero, but maybe this.
Oh, the beginning part, right?
Yeah. Maybe it is redundant, but I'm.
Yeah. This is just like it should be X0 plus the displacement. Yeah, okay. To be more precise. Yeah.
Fine.
Yeah, thank you. Okay, now this is a demo. I think I have to run the movie. Okay, so this is what typically happens in generative model. Okay, so last example, this is made by my student. I think he's very good at coding. That you could say I start with some complicated data distribution like rows, And then you can apply a sequence of this little transformation, and each of this is going to move the points on the rows a little bit, and it's going to convert into some target. In most generative model, the target is Gaussian. Okay, and so you can see become rows and into this Gaussian, but you can also go back, right? So in generative model, you want to go back because once I learn how to convert the rows into the noise, then I can take the data in the noise domain and convert it back to the data, so I can have the generation capacity. Okay, so yeah, in this example, yes, in this example is 2D, and yeah, of course, most of the real data is going to be much more high dimension. Okay, great. All right, so next is all right. So that's basically what I shown there is that particular example is driving towards Gaussian, and so this is most of the problem that the existing generative model is solving. Is you're trying to say I'm trying to move my data distribution from some P to some target, which usually is a Gaussian, and then be able to go back. So essentially, most of the existing generative model is solving this problem. Okay, this optimization problem. And so this actually corresponds to the so-called dynamic formula of the Wasserstein 2 problem. But our problem actually is slightly different in the sense that we also have this T representation, right? This tells us how to move my data points to change the distribution. However, the difference is we actually don't have a Q that's pre-specified, but we specify this through some L. So you drive the distribution to make it even worse. Okay, so that's the main difference of this approach from the existing generative models. Okay, now let's see how, give some examples maybe. And so, all right, let me maybe just to take one pause here. Now, once I have this, right, so how do I understand my algorithm? My algorithm is going to be, my T now is going to be consist of, representation using the velocity field that are neural networks, right? So when I perform numerical integral, that gives me the T, right? And when I do gradient descent, minimax, okay, sorry. And so we can actually solve, minimize with respect to theta, and the max part is going to be tuning the parameters of the neural networks in my generative models. Okay, so that's my algorithm. All right, let's see. Here's some examples to showcase how this performs, the GDA. All right, so we can see that in this example, I consider the classifier, right? I want to find the generative model that can maximize the loss, which is my classification loss. And this shows that, this is my, final kind of response to make it worse, and do some intermediate step. But importantly, you can see the convergence behavior is indeed converging in terms of the loss. And in this example, the loss is actually non-convex because this involves neural network, but you can see it still converges using the GDA scheme. And here's an MNIST example. And so this is much higher dimension than that 2D example. We can see the losses are converging. The first panel is the gradient with respect to theta. Right? The second panel is the gradient with respect to T. And the third one is the overall loss, but you can see it's all converging. And what this gives us, so here this trajectory shows, right, if I solve the GDA iteration, and then, for example, for the MNIST, you can see it gradually moves the digits to confuse the classifier, right? So, for example, you can see this 7 become a 0, okay, at least to my eye, and then the 9 becomes something like a 0, and so on. So, roughly speaking, intuitively, you can see by this GDA iteration, it's almost like a GAN type of approach, right? So, you train the generators that gradually try their best to confuse the classifier, but it's gradual, so they capture the whole dynamic process. And so, this is the CFAR example. You can see the track become a fog, and horse become a truck, and so on. And oops. Okay, so this is another example. You can see, for example, this is the animation. You can see how, for example, a sample of the picture of the dog gradually become a frog. This is what the sequence of gradually converted into the worst case samples. Okay, so here's another example. Remember, I said I want to solve this as a gradient descent ascent GDA approach versus the elimination scheme. And so it turns out, I think the interesting part from this experiment is indeed you don't have to do the elimination scheme because it's more expensive. Elimination scheme is that I have to solve the inner loop, right, which is my worst case distribution, to be precise, before I move into theta. But in fact, we show that you just do alternation, you can have very similar results. You don't have to do elimination. Okay, but the efficiency is much, much higher, right? So this one, you can see I achieve a similar convergence behavior, and this one takes on the order of 1,000 graduate evaluation, but this one only takes 751, so much more efficient. Okay, finally, the theory part, I think. This is probably most interesting to the audience. Okay, so what can we prove? And how much time do I have? About 10 minutes? Okay, great. So 15 minutes. Okay, great. So what can we prove about this? So hopefully, let me recap, right? We solved this minimax problem. And so we have we want to find the best decision against worst case distribution. And then with this loss inside. So the first one is a loss chosen by the user by problem, right? So it could be a classifier loss or something else. And the second one is the regularizer. And the lambda is the magnitude of regularization, right? So lambda, if lambda is bigger, it means that I want to stay closer to my P. But if lambda is small, it means you can go away from it. Okay? And so what kind of problem we want to solve is we want to consider this L that does not necessarily have the strong convexity concavity structure. Okay, NC problem eventually. And so in the literature, this Wasserstein Yao problem, most of the results established are for strong duality, means that I have to assume strong convexity concavity to exchange the minimax. Okay, so here we want to go beyond this and see what can we say about it. Okay, so I added some more references here. And I also want to consider the setting where, because if you have a non-convex problem, then minimax and the max mean may be different, right? So I want to see, for both of these two versions, the first version is the inner is max with respect to t. So this is like I find the worst case distribution first, and then I find the best decision against it. I call this t fast. The second version is I switch the two. And then I first find the best decision, and then I find the worst case to mess up with that, right? So I'm going to consider both versions.
So you agree that the first one is the defense, and the second one is for your perspective?
Yes.
The first one is the defense, and the second one is the attack.
Is the attack? Yes. Okay. All right. So we treat this as you can think about this as a Stackelberg game, right? So who plays first? Do you attack first or do you defend first? Actually, if you have a non-convex problem, they can be different. And so we want to show this for the most general loss, hopefully, eventually. Of course, it's difficult. I'm not saying you can say everything. We have to make assumptions here and there. But hopefully we can say something here. And second, we also want to show this for lambda that are both small and big. So what does it mean? So most of the existing literature actually is for lambda that's big. Means that I want to stay close to my reference measure. Means your attack is weak. Okay. But as you can imagine, I want to hopefully eventually say this for all the possible attacks, small attack and big attack. But the problem with big attack is you're staying far away from the P, and your problem is non-convex. So non-convexity comes from two parts, right? One is because my L can be non-convex, non-concave. And the second is because when my lambda is small, you're moving away from the P, then the problem actually is non-convex. So you want to handle that. The main challenge here. Okay, so the first result we've shown is to solve this minimax problem, the T fast means you have the inner maximization with respect to T. And we can show that under non-convex PL condition, okay, PL means with respect to T, we can prove this kind of linear convergence, which is the kind of standard kind of results. But keep in mind, this is not convex. We're not assuming any strong convexity here. Well, at least so this one, PL.
Both
No, sorry. The main part is NC. And then the inner side is PL. So PL, of course, is slightly weaker than strong convexity, right? So the outside respect to theta is NC. And so we can show that the GDA will find the stationary point, epsilon stationary point with epsilon squared minus 2 iterations. And of course, this is the main results, one of the main results. What are the assumptions here? Okay, so this is proved under first, the L0 smoothness of the loss function. So you can see actually, although we don't have convexity, but we try to push the boundary a little bit, right? So to not directly using convexity, but something weaker than that. So the first one is L smoothness of my loss. Roughly speaking, this is like consider the partial gradient of my L with respect to theta and the second argument involving data, and then saying that the gradient vector is L0 smooth, right? It has Lipschitz constant L0. And then the second one is going to assume the induced expected loss is L smooth. This L is related to L0 parameter. And also the lambda shows in here. You can see this is actually, how much you want to regularize. And the third one is going to basically consider the T that is PL. Okay, this is, I think, something that's different from the standard vector case. Take a step back and think about this minimax problem. One decision variable is theta, that's vector, but the other decision variable is T, because we want to capture the Q, right? So the T is RD to RD mapping, which is functional. So this part is probably one of the main contribution that's interesting in this problem is we have this PL condition in the T. So roughly speaking, is we have to massage this very carefully into our requirement of the T, okay? And so I'm going to give some intuition.
I have again a question.
Yes.
Do we assume that I have a noisy oracle in my gradient, or I assume that I get a perfect stochastic oracle, meaning?
Good question. Yes. This is population version. And we're not doing any SGD. This means this guarantee.
Okay, so it's
no SGD. This is population. SGD is no. We haven't solved that. Yeah, the students and great. Yeah, students can attack that. So this is only the GD version. Okay, so that's why it's epsilon -2. Otherwise, you don't have this. I'm sure you're familiar with this. And so, but by the way, what is kappa here? Kappa is a condition number. That's L over mu, right? So you can see this captured the geometry. The loss function is L smooth, and this kappa is basically the parameter of my PL. We think about this as a modulus of the convex function. Okay, so this is a reminder. What is the PL function? Roughly speaking, this is saying that I don't require my loss function to be exactly convex. It can have some convexity, but it's not too far from it. Okay, so we have, we require respect to the T is PL. And okay, so that's the first result. The second result is, let's consider the other version, max over T, minimax back to theta, okay? And so then this max mu problem, we can show, first of all, for the NC-SC problem, you can see the NC is non-convex with respect to T, but it has to be strongly convex with respect to theta. Okay, so this means that if I pick a T, then you can have a unique minimizer with respect to theta. Okay, we sacrifice a little bit to make it tractable. And then by choosing these proper step sizes, the GDA can find a epsilon stationary points using, again, epsilon -2 iterations. Okay, so, but this is not SGD, this is the GD version of the problem. And again, I think what's interesting is this part is new. Okay, so how to capture the T part, right, involving the functional. It turns out we have to introduce this, condition, which is we have to consider a good subset of transport maps. Okay, so what does this mean? This means that I have to consider this transport map. You can imagine, right? There can be some really bad transport map, completely mess up my geometry. But this is the transport map such that if I choose this map, move the data according to this T, and then, the curvature is not too bad, right? It's nearly convex, okay, for this. And yeah, so under this assumption, we can prove these results. And so let's give some intuition. What does this tell us? And for example, what is a good subset of transport maps? And consider a very simple least square regression problem. That this is my loss function here. And then, if I just consider a very simple T, which is not doing anything, okay. And then what is going to be the second order derivatives back to theta, and is XS transpose, the covariance matrix. So this means that as long as my data is well behaved, right, it doesn't have to generate covariance matrix. And then this is a good transport map. Okay, so this is a good transport map. But sometimes you say that, this is not doing anything. Is there any transport map actually has value? Okay, so this is example to show the transport map actually can help. If my data itself is poorly conditioned, means that the covariance matrix of my X degenerate have some zero eigenvalues. And I can probably find some transport map, for example, the polynomial maps. It maps the feature into X, X squared, and so on, and such that you can make the covariance matrix after transformation to be non-degenerate. This is, I think, why we use feature maps involving kernel and neural networks that can improve the condition of the problem. So this is I think the concept, roughly speaking, why we need this T. Okay, finally, this is the last result I want to present. Is, as a premise, we hope that we can push this as much as possible. Where can we push it to? And so the final version we consider is it's non-convex, non-concave. Okay. And so with respect to the theta is non-convex, with respect to the T part, it is non-concave. Okay, so this is the most difficult problem. And so here we say, okay, if you can do a little bit of smoothing, means that if I smooth the transport map side by introducing some L2 regularization, and this is the idea behind a lot of these proximal map idea, and we call this in particular one-sided damped PPM. PPM is proximal map methods, and then we can prove again similar results of the convergence epsilon -2. But it's one-sided means that we only adding this regularization on the T map. The theta part is actually okay, so we leave that as it. Okay, all right. So I guess yes, sure.
One thing, I didn't interrupt you before to complete the results. When you present the stationary point, you have two parameters.
Yes.
Now that can mean many things. What do you mean? Because one thing for minimization could be the first derivative and the second derivative, or the one parameter, the mean parameter, and the max parameter. What did you mean with alpha, comma, beta in the parentheses? Like you say epsilon.
Oh yeah. Right. Okay.
What did you mean with
Thank you for asking the question. So this means that it has two arguments, right? Exactly like you said. One is theta, other is T. This means I solve the theta such the gradient, the norm of the gradient with respect to theta is less than epsilon. This is the norm of the gradient with respect to T is less than this. So for convenience, we choose them to be, this is scaled by the condition number, which is kappa defined. It's a constant. So this is control the gradient with respect to both parameters to be less than epsilon.
Philosophical question, but I would like an answer from someone that does application.
Right.
The problem is non-convex, so for sure you cannot find really local minimax points. The guarantee says that you find the point that it is locally stationary.
Yes.
So actually, even if you do GDD, you will be also happy because you can find the minimization. You can find the point that makes small gradient of the one and small gradient of the other.
Mm-hmm.
And from math perspective, you will get also a guarantee similar with that. Now the question is, did you run the experiment?
Yes.
That says that the GDA, the idea that at least I'm trying to have that min-max idea,
yes,
gives me something better. Do you understand my question?
Yes. So I think maybe one thing that's in this experiment that we're trying to say here, which is it's not that, so what can theory tell us, right? So is this like just the vacuous, versus they said this actually says something useful? I think this is, one, I think such experiment trying to say this. Because you could say if I solve elimination, I say let's solve the inner maximization to be less than epsilon first, and then I eliminate entirely in that sense. And then I solve the outer loop, right? And of course, this is going to be expensive. And think about the T itself. This T is represented by neural network. This I have to solve, many iterations until my neural network parameters converge. Very expensive. And this is the behavior I have. You can see this is the norm of the gradient back to the parameter of my classifier. This is the norm of the gradient back to T. And so they're converging. Good. And so this takes 1,786. And this is a simulation with only two-dimensional data. Okay. There's many iterations of the gradient descent. But using GDA, this is just alternating between theta and T. Theta and the T means that I haven't fully solved the inner maximization problem at all. But you actually have a similar kind of behavior in terms of convergence. And also you converge to actually similar quality of the solutions. And the number of gradient evaluation is 751 only. So you save that. I think this is probably, the theory says the GDA is going to converge, but it actually moves quickly, right? So the inner maximization hasn't been fully solved. You already moved it's actually convergence though.
But if you observe, even in your experiment, what is happening is what you are plotting us is the norm of the gradients.
Yes.
So to make the norm of the gradients of a loss small enough, I can do a minimization task, and it will give me again that thing. So what I'm requiring, and it's maybe beyond of the lecture, but
Sure.
I'm asking that because I'm working from theory perspective.
Sure.
Is the following: is at least in practice the idea that I'm doing GDA, which gives the same guarantee with GD.
Yes.
From math perspective, is at least experimentally the GDA better than GD? Maybe you don't have this experiment, but take it as a...
Yeah. Thank you for this. Yeah, we can probably discuss offline. Be happy to chat more about this. Yeah. But I think this part, this experiment makes it quite intriguing to us. This is like you're moving very quickly before you solve the inner maximization entirely, you move on. And actually, maybe I should mention that this another part that's interesting, maybe in terms of theory, is when we prove the NC problem. Commonly used assumption is interaction dominance condition. In this problem, because one argument is the probability distribution, we actually have to introduce a new notion of average interaction dominant condition. Because it's minimax, actually, it is not trivial because you could totally mess it up and explode, right? So I think that's probably the main value of this. Okay. Yes. Not in this problem. So this is unconstrained entirely, yes. Because we put the constraint into the regularization part, but it's not a hard constraint.
Possibly I can partially answer an honest question. I mean, if you use like BDD, like naming algorithms, because you have this regulation, and this one function is not bounded below, so if you use
okay.
Yeah.
Okay. Oh yeah, that's thank you, Javed. Yeah, maybe I wasn't sure I got your question entirely, but yeah, it's you can totally explode if you don't have anything here. Okay, great. So all right, so I guess that's all I want to talk about. What I think what's interesting here is we have this minimax problem that's inspired by finding the worst case generation, and it is actually useful in the end that I have a generative model that is captured through the T. Okay, that give you samples out of some worst case distribution. You see these pictures of the dog become a frog, right? The frog is a worst case sample. And I can generate many samples, as many as I want, because essentially it's a generative model. You can convert noise into worst case samples. And so I think what's also interesting is this is a type of minimax problem that's not in vector space. The T is in functional space. Okay, so this because of that, in terms of developing theory and convergence, I think this is some new problem, new challenge here. Yeah, and also I think fundamentally it's probably related to computational information geometry. I call it computational because information geometry is a classical framework introduced by, I think, Sushi and Marty in the early 2000s. And there, I think they have beautiful theories saying, how do I consider distributions on the manifold, right? But then now we have a computational framework that can actually find the solutions on this, geometry of distribution manifolds. Okay, so this is very new work. Like I said, I just posted on arXiv this morning. So thanks for all your feedback. If you have more discussions and questions, I'll be happy to discuss offline. Thank you again. Oh, yes, question?
Yes,
Thank you.
Reason between this approach and traditional adversarial training formulation where take each of the sample.
Yes.
Maximally.
Right. Yes.
So the only difference I can see from your formulation and the standard adversarial training formulation would be there they have sample by sample.
Yes. This is not a sample by sample. This is generative. Yes, you can generate many.
Take this kind of version get this transformation version of the formulation. Basically, what you're doing is you're looking at the normal constraint to be bounded by something.
Yeah.
That captures the total amount of transport code.
Yeah.
Yes. Traditional adversarial training captures about
maximum per sample transport.
Yes, yes, yes. Right. Yes.
The question is basically like which one is more efficient?
We actually have a comparison
I see.
in this paper, even like in 2024 paper. And exactly like you said,
Basically like W2 Wasserstein versus infinite Wasserstein.
yeah, it's a little bit like that. Yes. And we can show actually in theory, first in terms of theory, you can show that this one will achieve a lower loss. This is a worse attack, worse attack. And exactly. And then in terms of actual performance, we can show this give you more robust because you have a worse attack. You have a more robust classifier in that test. Yeah, but that's a good question. Thank you all.